ensuring that multiple conditions are true before allowing an action. So, if both inputs are true, both inputs are 1, it gives true, so 1 at the output. If one of the inputs is 0, it gives an output of 0. The problem is that all modern computers implement so-called irreversible logic, which means once computed, you cannot run it simply backwards. You cannot reproduce the inputs. Looking back at the gate, if I know that I have 0 at the output, and I try to run the operation in the reverse, I can't reproduce it. Even when I know that the output is 0, I'm still not clear what the input was. There are many possible combinations of inputs, which gives me 0 at the output. This kind of logic is irreversible. So once it's computed, it's gone, and you can't get it back, and the most important, the energy is wasted. But what if we can build a computer where we don't waste any information? Can we then recover this energy? Landauer himself proved it was possible. He found that the loss of energy was due to the destruction of information, not from the execution of operation itself. So if we were able to build a reversible computer, theoretically we could compute using no energy at all.
It turns out that when you use reversible computing, you can really kind of decouple the generation of heat from the processing of information. And it's difficult to translate that into kind of terms where we could construct logic, but when you figure that out, it then allows you to, in principle, significantly reduce the energy dissipation, thereby the energy consumption of computing.
At first, it's really hard to comprehend, just because most of the things we experience in our lives are irreversible. Take aging, for example. Or when you pour hot coffee in a mug, it spreads heat to the mug, right, and into the air, and the coffee is cooling down. And it's irreversible without external intervention. And we know that from the second law of thermodynamics, which says that the total entropy of the system either stays the same or increases, never decreases. What is even more interesting, that the most fundamental laws of physics are reversible. Means if you know the state of a closed system at some point, you can always run it in reverse and determine its state at any previous moment. If we take a game of billiards, for example, if you film it, it would look normal played forward or backward, because the physics of collisions is the same, so you could easily predict their past or their future positions. And the same reversibility holds for quantum computing. Take D-wave quantum computer, for example. Quantum gates are always reversible. Couldn't we just apply the same principles to conventional processors? 60 years ago, Landauer considered this idea impractical. Back then, if we wanted to make computation reversible, we would need to store every input and every intermediate result, and doing so would quickly fill up the memory. But later on, his colleague, Charles Bennett, found another way. He thought, what if instead of just storing intermediate results in memory, once the result is no longer needed, one could just reverse the computation. This has a huge advantage, because in this case, we only need to store the result of the operation and one of the inputs, and then we can reverse it back. Let's get back to our example. If we take the AND gate and add an extra output, copying one of the original inputs, then knowing these two values, we can reverse the operation. If I know that the output is 0 and one of the inputs was 1, I'm immediately certain that the second input was 0. With that, I can reverse the operation or decompute it, getting back the energy that was used in computation. Of course, at the computer level, it's way more complicated. But in principle, we understand now that it is possible to recover the operation, to reverse the operation. But how does it help us to get back the energy? Let's have a look. There is a startup that is building the first commercial reversible computer. This computer chip implements reversible logic, which we've just discussed. So they took the standard logic gates and adjusted them to work in reversible fashion. And typically it's quite a hassle. But in this case, it's good that this is compatible with our traditional manufacturing process. And of course, these gates are still take energy to switch from 0 to 1. But the trick is, as long as this energy is not dissipated as heat, but stored in the transistor, they are able to recover it at the decomputation step. And they're getting close to it. The first prototype is coming out already this year.
It's kind of interesting. So normally reversible computing requires both a forward and a backward step. This isn't quite necessarily true. So it kind of depends on the paradigm of reversible computing you're considering. It is the easiest approach to do reversible computing, where you compute one step forward and then one step backwards. And this is because you can embed kind of any traditional algorithm that we've already developed over the last 100 or so years of computing. You can embed that in a reversible computer by kind of computing it forwards, saving the output, and then decomputing kind of all of the intermediate and temporary data that you generated. And so kind of this allows us to just automatically reversibilize anything that we already have and save almost all of the energy.
Now, let me guess what you're thinking. How does computing twice help us to recover the energy?